So we have a list of questions that we've collected, but let's start with the first question. The first question is, how did you start writing Gurobi? What were the first things you implemented? And how long did it take to get the first Gurobi version? And how many lines of source code did it have?
Okay, so I take it. So, I mean, it's relatively simple. We left at, three of us left iLog 2008 and working from home. And we just bought some computers, hardware, and install some VM with Linux, and then start to write the code. And we focusing on MIP and parallel. I mean, because that time multiple computers become widely available, and we considered data science as an important area, and so we also developed Python. So first thing, I started to develop CPLEX. This is, I mean, LP is important. Also, CPLEX is crucial for MIP. So I write CPLEX code while implement the MIP framework, parallel, branching, and bound. After that, then both of us working on other parts of MIP, including cuts, heuristic, and presolve, and then API. And it took us about 10 months to finish first version. And it has, how many lines? About 82,000.
82,000, something like that.
Yeah, and now currently 9.0. I just count the engine code. The C code is about 9 times bigger. And I should mention the source code line is not good measure about the work for software development. I mean, usually nice, careful design often will make the code more concise. Nice, for example, we introduced attribute and handled the parameter nicely and make our code shorter, especially if you look at our C++ source line. I mean, whole source line is are less than CPLEX header file. So hopefully I answered the first question well.
Yes, thank you.
So we had actually, so one of the nice things we had, which, you know, it seemed kind of daunting at the time, but we started from a blank piece of paper. And so, you know, we'd been working on LP and MIP solvers for a while, but this was an opportunity to start from scratch and, you know, take a step back and think about how we wanted it to look. And I mean, we had a pretty big, strong focus on simplicity early on. We were trying to keep it as concise and simple as possible. A lot of that was just necessity. We had a lot of code to write, and so we just we tried to keep it as simple as possible. But I think that's served us well over the years.
Yeah, and a start from scratch is always nice.
Yeah.
And also, I mean, look at the new architecture and forget the old stuff. That's nice.
Okay. Next question we have is, after you've created CPLEX, at which point did you realize that MIP was the key to industrial applications? What triggered the adoption of MIP in industry?
Well, if I may go back a little bit further, it was already true in the 70s that MIP was widely recognized as an incredibly powerful modeling tool. The problem is you could model things, but you couldn't solve anything. And there was kind of some disillusionment that resulted from that. Moving forward, CPLEX was started in 1988, I guess. Initially, all we had was a simplex solver. It took us about 2 years to recognize that to be a player in this space, we needed to have a MIP solver. So that's when we started building a MIP solver. Moving a little bit forward to, say, the mid to late 90s, that's the period of time at which CPLEX, in my view, started to to be the dominant solver in the space. But I don't think you could have said at that time that we had the best MIP solver. The strength of CPLEX at that point was based largely on the business model that we had and the simplex solver that we had. For me, the point in time at which MIP really became what it is today, and the dominant application that people were interested in, was in 1998 with the introduction of CPLEX 6.5. That was exactly the point in time at which Gu and Ed joined the team, and they added an enormous amount of functionality into the solver. At that point in time, I think we measured in one release there was a 10-fold improvement in performance. And perhaps more important than that, I think in a certain sense that was the turning point in the subject. That's the point in time at which I, for example, really started to believe that you could solve general purpose MIPS robustly with an out-of-the-box solver. And just to repeat myself, that's when things really took off. So my answer is 1998, CPLEX 6.5.
Thank you. Okay, so next question is from Matthias Rost. He wants to know, he would be interested in quantum leaps for solving MIPS. Where do you see the potential in the future to speed up computations?
Well, I'll comment on the quantum leaps. I think Gu can
add a comment.
Yeah, what's coming in the future. So for me, there were really fundamentally three quantum leaps that contributed. The first was, and this happened sort of in the mid-1990s, was the development of robust dual simplex solver with some version of steepest edge. That's when the dual simplex solver, which is the workhorse in the computations that MIP does, really became essentially what it is today. The other two biggest things for me are pre-solve, the development of pre-solve, which continues to get more and more important, and the introduction of a wide variety of cutting planes, most importantly, the Gurobi mixed integer cuts and mixed integer rounding cuts. Again, those are the three big quantum changes for me.
Yeah, I would say since then there haven't been really big quantum changes in the sense. So MIP is really about a large number of small improvements, I would say. But those add up very nicely every year. And each improvement may be a general improvement that helps a little bit, or maybe a very nice improvement that helps on a very specific class of problems. And whatever problem type you have, you will benefit from one of those, and that makes it faster and faster all the time.
I think the search part made it sound good. I mean, so-called dynamic search helped quite a lot. But it's always hard to predict the potential in the future. I mean, each time, it's just hard to predict the future. Future always something will happen, but it's hard to predict, I would say. And now is more a bag of tricks. That's, something in pre-solve, something in cuts, something in heuristic, and also something symmetry or others.
Yeah, this somehow gets in, a bit into a question that comes up a little bit later about, will this exponential, if we can call it that, exponential improvement in MIP performance will continue. And this is a question we get every year. It's the same question. We've been getting it for 10 years. And our reaction every time is it's getting more and more difficult to achieve improvements in the MIP. And nevertheless, when the next release comes out, there are, as Toby put it, a whole collection of new ideas that contribute to a significant improvement. And it's been continuing that way for, actually, if you go back to the CPLEX days, it's been continuing for 25 to 30 years at this point. The guys who are doing the development really continue to just come up with new ideas. Most of them, as Toby said, small ideas that just add up to significant step forward in the end.
Very good. Okay, next question is, does Gurobi have any plan about launching a verified certificate exam or other kind of educational materials in the future?
Yeah, so we don't actually have a formal training program at this point. So we do events like this one, but in terms of multi-day, here's the curriculum, and start here and end here, and now you know how to do optimization modeling. We haven't taken that on. So, and actually, the Informs has had some efforts to do some OR certification, but we're still pretty far from as a company from being at a point where we want to try and actually put our stamp on a particular curriculum, a particular approach to becoming an expert in what we do.
Okay.
On the other hand, I say, which is a little bit related to this question, we now have these optimization application demos online, and they can serve as a really nice resource for classes and optimization. And of course, this doesn't mean that we will get you a certificate for that, but that's something that people can use and get in touch with Gurobi in their classes.
I would also add, we've got a series of videos on YouTube, also on the Gurobi website, for targeting primarily data scientists, but any beginners at math programming could learn there. Okay, so the next question is quite a different one. Is Gurobi considering making a conic solver?
So I take this one. I mean, conic, let's say first order conic is about LP. The second order conic is about convex quadratic constraints. We support both. And there are some other conic combs like SDP or power comb, mosaic supports, or other solvers support. We are considering, but not in the near future. Like this year, we won't release anything about SDP or power comb.
But we are going to have SDP cuts for non-convex problems, but of course that is not an SDP solver in there.
Huh.
The next question is, are you considering integrating alternative approaches in Gurobi, for example, CDCL, SAT, for binary subproblems?
Yeah, so I think what the question is about SAT solvers that use conflict-driven clause learning things. Yeah, so we have such an idea already since quite a large amount of time in our backlog of ideas to try. We do have primal heuristics that work a little bit like a SAT solver, so local search on pure binary problems. And we also derive conflict clauses from infeasible subproblems in the search tree. So in this sense, there is conflict learning going on, but essentially all we do is heavily based on the LP relaxation, and that for this reason, it's not really a SAT solver. But there are a small number of problems that we have in our test set where applying a SAT solver would really solve the problems very fast. But for now, we did not yet figure out a way of doing that without hurting overall performance in general. So Ed, you have worked on this binary heuristics a little bit. Maybe you can comment on this as well.
Yeah, so the main thing that sort of holds us back from looking at SAT specifically, or actually several different very specific problem types, is that it's common, even if you start with a SAT problem or a problem of a very specific network flow, something like that. It's common to at some point want to add a side constraint, so a new constraint. And then in contrast to MIP, so in MIP generally you start with a MIP, you add some constraints, and when you're done you still have a MIP. When it comes to a lot of these more specialized forms, you start with that specialized form, you add some sign constraints, and all of a sudden now you have a MIP. And so we just, in general, we just haven't put that much effort into very specialized problem types.
Okay. Next question comes from Jonathan Jacob. He asks, as more applications are being developed for cloud infrastructure, does that change how you perform R&D? How dependent is your R&D on hardware?
Yeah. So when it comes to cloud infrastructure, it's primarily a deployment question. So basically, what does it take to deploy an application on the cloud? Because the machines on the cloud are the same, they're basically the same machines that you'd have in your server room or at some level on your desk. And so, we've been looking at, we've got our instant cloud, we've got compute server. We've been working pretty hard to try and figure out how to make it easier to deploy in the cloud. Actually, and then there's just the question of, with the cloud, you can just go and grab 100 machines like that. And so actually, maybe I should hand off to Toby just to talk a bit about what role having access to lots of machines plays in our.
Yeah. So when I joined, actually when I joined CPLEX back in what was it, 2006. Then I started developing, and they were asking, here you need more machines, and I said, I have my desktop machine, so why do I need more machines? That's just fine. And then I pretty quickly realized that is certainly not enough. And now when I joined Gurobi now in 2014, one of my first questions was, so what is the size of your machine cluster? And then I got the answer. Back then it was, what was it, like 24 machines or 30 or something like that? And then I said,
the initial cluster was 24, yeah.
Right. Well, that's certainly not enough. And then we relatively quickly got a new one that has 60 machines. And now we got an even larger one that has 192. And even that is sometimes not large enough. So you can't have enough machines for MIP development because the machines are most often the bottleneck of all of our development process. So so my main task in my life as a MIP developer is to keep the machine pool busy with ideas and running tests and stuff like that. And sometimes 3 or 4 or 5 of us are running experiments at the same time, and then the machine cluster is busy pretty.
We've got
pretty much. Yeah.
I just checked. We've got 6,000 jobs in the queue right now.
Oh, really? Who's running stuff right now? So I'm running a new master right now.
I'm running some stuff as well.
I think this might be an appropriate time to talk in a little more detail about the development process, the way ideas get evaluated, and the way in which decisions are made about including these ideas in the code. I mean, some of these ideas result in improvements that are like 0.2%. Yes. You have to somehow be able to recognize that, to come to that conclusion. Toby, maybe you could comment on that.
So our regular MIP test set has about 3,900 models right now. And if you really want to measure a performance improvement that is in the order of 0.5%, then just running these 3,900 models is just not enough. So because when you use multiple seeds, it could be multiple different random seeds. It could be that on one seed, the difference is a 2% performance improvement, while on the next seed, you see a 1% performance degradation. So you can't really measure 0.5% with just 3,900 models. And for this reason, we use nowadays always 5 different random seeds. So that means one full set, full test through our test set is about running 20,000, almost 20,000 individual MIP jobs. And even then it is sometimes hard to measure small performance improvements. And then it's not only about, so for accepting a change or rejecting it, it's not only about the numbers that come out of the benchmark experiments, it's also about whether the development team thinks that it should be a good idea, or there is some theoretical reason to believe that it is good, and also whether it makes the source code nicer. So, for example, if a change would actually remove in total lines of code, then that is a positive change in a sense. And all this has to come together before we would accept a particular change to the code, because of course, every change has some risk that it breaks something else. And so we only want to get changes into the code that really add some value.
Yeah,
Okay.
By the way, there was a one of the Informs meetings, maybe it was 2-3 years ago. The development team, for the presentation we made in our regular workshop that happens, a couple of days before the actual Informs meeting itself starts. In that presentation, there was like 2 or 3 slides with literally a list of, at a high level, of the things that had been introduced and some sub-bullets with percentages next to them. And I personally found that those couple of slides just gave a fascinating view into the way we make progress with mixed integer programming.
Yeah, I think the biggest number was something like 3 or 4% improvement from a single change or so. And then I remember there was one change where I only changed 1 digit, so 1 character in the source code, so 1 number, and that already gave like 2%. So that was a nice one.
Actually, since the original question was about the cloud, one detail maybe worth adding is that, so people may think, well, now that you can just go grab 100 or 1,000 machines on the cloud, this must make your testing a lot easier. And we actually don't do any of our testing on the cloud because we're looking to measure, 1%, 0.2% effects. And when it comes to these cloud providers, these are shared resources, and in a lot of cases, actually, they're perfectly happy to substitute out a different machine. If you ask for a machine with a certain speed, they're perfectly happy to say, well, we don't have any of those, but we've got one that's even faster. So good news, you get a free upgrade. Sorry, go ahead.
Yeah, I was just going to say, when we buy new machines, when we buy 196 new machines, we pay a whole lot of attention to making sure they're identical. And somebody else could probably comment on this better than I, but we do some tests to make sure that those machines are very close to identical in performance.
Oh, sure. Yeah, we make BIOS. We got to make sure the BIOS version is the same across the machines because we're looking for that level of precision. Yeah.
There is a related question. I'll jump down to it. It asks, how do you find new algorithmic tricks?
So I can comment on that. And usually, I would say first is from public source, publication or papers and talks at conferences. And then we attend the conference and get ideas, and we work on those ideas, try them and verify. That's one thing. Other is now, we see less and less research on LP. Also now, not much research on MIP. Then we still need to improve our LP MIP solver, and we do called internal research, and we look at important aspect of MIP solver like pre-solve, cuts, and we focus on that, try to find the idea to improve. Other thing is, the model, study model is the important one. And we often get a request from our customer, although they give us very large hard models they want to solve, like in few minutes and push us, and then we need to study the model, and also for benchmark model or other model we look at. Often you look at it, you will find some idea how to do some reductions to make the model smaller, or you can generate some cuts tied to the formulation. And then how to evaluate the performance. And I think Toby others already covered. I mean, we have a cluster, several cluster of computer, and we use that. And I mean, we don't just run the internal set. We also, I mean, for example, use 5 random seed to make sure the idea really improves.
So what was if I may ask, what was the last time something got included in the code, made a significant difference, that an idea that just came out of the academic literature? I think it's been a while.
I would say we still get some. I mean,
some?
Yeah, especially the quadratic one. And
certainly in that area. Yeah, I'm just talking about the MIP solver.
MILP is not, there's not so much anymore, I would say.
Yeah.
So the majority of the MILP improvements really come from looking at models that we got from the users. So one particular example we just had recently, which is, I would say, typical. We got a model, a very small one, that was actually a non-convex MIQCP, where the user, I think it was an academic user, reported that we have a bug in there because there was an obvious solution. The zero vector was feasible, and Gurobi claims the model was infeasible. And then we looked at this model and relatively quickly found out the issue and fixed the bug. But as a side result, so our colleague Michael Winkler looked at this model more closely and then inspected what we had as a pre-solved model. And then he actually found, I think, 2 or 3 things in this pre-solved model that were kind of stupid, where we were actually missing a certain pre-solved reduction. And then from there on, you can easily see why this particular pre-solved reduction was not found. And then we can implement it, and then we tested whether it is actually improving on our overall test set. And that, again, gave in this case, on the non-convex MIQCP test set, I think a 5% performance improvement, just triggered by this one tiny little user model where we had a bug.
Okay. Next question is there a benchmark between Gurobi versus D-Wave on QUBO problems?
QUBO and D-Wave.
This is quantum computing. So there was actually some early work comparing actually CPLEX against D-Wave on QUBO. QUBO is quadratic unconstrained binary optimization. And I mean, to be blunt, they made kind of a mess of this whole thing because the comparison was not really, it wasn't a fair comparison. It was looking at time to find a heuristic solution in one case versus time to find an optimal solution. It wasn't the best formulation. Frankly, I've lost track of benchmarks of D-Wave against Gurobi or against MIP for QUBO. I mean, one thing to keep in mind is people from quantum computing often ask us, so what fraction of your customers are solving QUBO problems? Quadratic unconstrained binary optimization, which is the problem that the D-Wave machine, the quantum computer, solves. And I don't know, so
no.
0, I don't know if it's truly actually 0, but it's certainly near 0. So,
but Ed, this is an NP hard problem, so you can translate every MIP into a QUBO.
Yeah, sure.
So just like you can translate every MIP into a TSP problem and solve it with Concord, which is a decent TSP solver.
But we still need to expect, the breakthrough in the quantum computer in complexity. That's still not sure. We are not sure about that.
I mean, there's interesting potential there, but we're still a ways off from realizing. Actually, one thing that's been interesting about quantum computing is just the attention that it's focused on optimization.
Yes.
Because you look at quantum computing, you look at the applications. So there's the two most frequently mentioned are cryptography, breaking cryptography, and optimization. And when it comes to optimization, basically the standard statement is, well, you can't solve these problems, so you need a quantum computer. And we solve these problems every day.
Okay, next question comes from Simon Felix. Where will ML algorithms first appear in Gurobi?
So I try to understand that question. Does it mean whether we will have something to solve machine learning problems? I mean, we have some example to solve. Like the regression that's used. The most common method or for machine learning. And if you means to use machine algorithm inside the MIP to improve the MIP performance, there are some research you can find and talks in Informs meeting or other meeting, but so far, result is there are some useful result, but generally not so interesting. And inside our code, we do have some learning stuff, but maybe not to the level of machine learning. Really using this approach, but it has some learning impact. But we don't restrict ourselves to some method. We just whatever works well, we will use and for the performance.
Yeah, so Simon just in the chat clarified the question. The question was actually about the use of this support vector machines for triggering CPLEX's choice of whether to linearize or not.
Okay, that's
the binary quadratic terms in an MIQP. And yeah, I was looking at this as well, and this is really interesting research. And it is nice that with the latest release, they actually made it such that it works in practice. But overall, I have to say, regarding machine learning, we are already doing that since years, right? So the techniques, for example, pseudo-costs in branching, or how to control the efforts spent in the various heuristics, or how to decide which pricing strategy to use for solving the node LP relaxations with the dual simplex algorithm, or whether to use the primal or the barrier for the nodes. All these are, so to say, classification problems. And we already use some dynamic strategies to learn on the fly which is the best choice. Here, so so to say, the new thing about the CPLEX study of the MIQP was that they produced data and then used offline learning and to come up with a rule and features and stuff like that and to control this. But in a sense, something like that has already been embedded in MIP solvers for quite some time. One of our research activities right now is to look at one particular problem in LP solves, which is whether you want to dualize the problem or not. So that is also a classification problem. And here we are looking at machine learning techniques. So maybe something like this will end up in the next release. But it depends just whether it gives a performance improvement in the end or not.
Yeah, if it works, we will add it. Yeah. If, doesn't work well, or if just something simple. We prefer something simple. If something simple work as well as it, we just do simple. Pick the simple way.
Because otherwise, if it's not simple, sorry, just let me
sure.
If it's not simple and you can't understand it yourself, why this would be a good rule, then there is high potential that you get into over-tuning.
Yeah, I think there's maybe a common observation, which is the more heavily studied a particular decision is, the less scope there is for a machine learning model. So that, you know, the thing that CPLEX is doing, the thing that we're looking at doing, you know, how to decide whether to dualize, how to decide whether to linearize. These are decisions that I would have to say they haven't received that much attention from us. And so just throwing a machine learning algorithm at it has some potential to find something. Whereas something like branching, that's, you know, that's been studied for 50 years.
Yeah.
That's a tougher problem.
Yeah, and the particular question of whether to linearize or not. So here the answer is, for most practical problems, it's almost always better to linearize. And so there's not that much room to come up with a rule that would actually not linearize the problem, because that's a risky thing to not linearize, because most of the time linearization is better here.
Yeah, I would add, I mean, whether dualize or not, I mean, sometimes we can using, I mean, parallel to decide, just to try both to decide.
But Ed, you say that branching has been studied for years and years. Still, it took a long time for people to recognize that branching on the greatest integer in feasibility was a bad idea. Right? It took a really long time.
Yeah.
That's true, because it's just so intuitive that it should be a good idea.
Yeah, indeed. I want to use this opportunity to just jump back a little bit, because one of the earlier questions was about quantum leaps forward in MIP. And I think I left out an important one, which is heuristics. So there are two, in my mind at least, there are essentially two kinds of heuristics. There are heuristics for finding a first integer feasible solution, and heuristics for improving on existing solutions. So of those two, the first one, finding the first integer feasible solution, is, in my view, still a great research area. We have algorithms for that. We have heuristics for that. But you could conclude that they're not great. Exactly, they're successful sometimes. If you switch over to improvement heuristics, there enormous progress has been made. And I think you could fairly point to this rinse idea that Ed played a major role in. I think that's was indeed, in terms of heuristics, a quantum jump forward. I mean, I should say, heuristics are difficult animals to measure, the effect that they have on solving. How much effect they have on the solve time for problems that we can solve to optimality is something one could discuss. But finding integer feasible solutions quickly clearly makes a huge difference in the adoption of mixed integer programming. It really completely changes the experience. So, didn't mean to end the discussion. Sorry.
Yeah,
Okay, so thank you. Goodbye.
I would say, Bob, I add one comment about the first integer solution. I will give Hans Mittermann some credit. I mean, he created the benchmark, and certainly people paid some attention, and we also paid attention. And I mean, that's, I mean, if you look at the CPLEX 10, that's really not much. And since that, and try, I mean, just, I mean, using parallel, I mean, do something and find the first solution, and before even solve LP, and then for the LP, do some degenerate move or something else, and a lot of stuff. And that certainly helped it also a lot.
Yeah, so competition helps the development. That's clear.
Yeah.
Oh, competition helps enormously.
Yeah.
Absolutely.
There's another question that's interesting also from Simon Felix. Where were the technical surprises for Dr. Achterberg coming from Skip? We're putting you on the spot, Toby.
Oh, yeah. I have to say, the big thing was to join CPLEX in 2006, because back then I was working on Skip, and I had a hard time, of course, competing against CPLEX. And when I implemented Skip, at the time it was CPLEX 9, and then I was able to be almost on par with CPLEX when I was using CPLEX as an LP solver. And then later, CPLEX 10 was not able to beat it anymore with Skip. And then I joined CPLEX in 2006, which was about half a year before CPLEX 11 was released. And then I was looking at the source code, and then of course I had the expectation that, yeah, that is so great and everything is so cool in there. And then I was looking at the code and thought, well, it's pretty much the same as in Skip. So all the components are the same components. There are some small additional ones but they are not that much important. So except for the parallelization, so Skip is only sequential in its core. But the main thing, why it is so much better, are really all those small little details. So for example, how to exactly do the aggregation in the MIR cut separation, that there are some additional important tricks that you can recognize certain structures beforehand to avoid a long running loop and stuff like that. All those tiny little details where you really, which I now know from our development efforts, where you really have to invest time to think about it, and in particular look at large customer models to really find all those places where you have a performance issue internally, and then test it or run multiple test sets and stuff like that. All those tiny little details, those make the difference. And then when I joined Gurobi, it was really not a big surprise anymore, because as you can imagine, so the Ed and Gu developed this code, so it looked, at least from a coding style point of view, very similar to CPLEX. So the opening and closing brackets were at the same places, and there's this quit jump point all the time to catch the error conditions and stuff like that. But for Gurobi, I think my biggest eye-opener, or which I liked the most, was how the parallelization of the search tree was implemented, in particular how this is done with calling the user callback. So that is really a nice thing that I liked a lot.
And the code may be simpler. I mean, maybe not now. Now it's getting more. I mean, because lot of things the code is old. You developed a lot of things, and then it's really hard to get rid. I mean, because still some customer use. That's difficult. So also yes. When we start, we immediately paid attention to parallel. Ed did a lot of work. I know Bob started CPLEX that time. Parallel wasn't that important.
No, it wasn't, and it was not. I was actually the person who implemented the parallel version of MIP in CPLEX, which is one of the reasons Gurobi is so much better. I had nothing to do with the implementation in Gurobi.
That time does not have multi-core computers. That's why. If you don't have hardware, it's harder to think about why.
I will gladly accept that excuse.
I'm going to skip to another one here that's a different subject. What is your favorite Gurobi parameter?
What's our favorite Gurobi parameter? Boy, that's a tough one to answer. Maybe in the context of just thinking how you would tune a model. So at least when I approach tuning a model, the very first thing I look at is the root solve. Usually it's not a big issue, but it can be an issue. It's one of the easiest ones to solve. The possibilities for the algorithm at the root are relatively limited. And every once in a while, Gurobi just makes a bad choice. It doesn't try barrier, for example. So that's the very first thing I look at. I just look at the root solve and make sure that we're not doing something silly, missing a simple idea. The next thing that I look at is the problem, when you just run defaults, are we getting much movement in the bound or not? And if it looks like the problem, there really is no way to move the bound, the first thing I look at is turning off a bunch of the cut ideas, because they just consume a bunch of time and don't seem to be contributing anything in some cases. So there, the cuts parameters in particular, you can use to turn off the cuts, and that can lead to big improvements. I like to, on the other side, if it looks like there's progress to be made in the bound, but we're perhaps not making as much as we should, that's the time to think about MIP focus equal 2 or the cut parameters to up those to do the opposite. And yeah, those are usually the main things that I look at initially. And well, one other thing, and that is if the problem is having a really hard time finding its first integer feasible solution, then we have a couple of specific heuristics, the zero objective heuristic and the min, I think it's called the min-rel heuristic, which you can easily set parameters to make sure that the code makes a more concerted effort to use one of those two heuristics to find, the initial feasible solution. That can sometimes make a big difference. That's my answer.
My most favorite parameter is the random seed. This is the one that I'm using the most of. And there's also a nice possibility to sneak in birth dates of my family into the Gurobi source code by plugging in those as random seeds for certain algorithms. So have you ever figured out how many birthdays of my family are already in the Gurobi source code? I guess not.
I would have said 0.
No. Many more than 0.
So
Yeah.
now, okay. I had to go ahead.
When it comes to favorite parameters, so there's actually in the code, there's some hidden parameters. There's some things that have been developed that seem like good ideas, but don't actually help. And so I think each of us probably have a few sort of favorite things to try, just in case this idea that you had that you think should help, this is the model where it finally proves that it's a good idea. It's actually a useful idea. So I think each of us have a few of those that they like to try.
Yeah. No-rel heuristic still a hidden parameter?
It is.
Yeah. For me,
there's also this. I failed to mention the improve start
Yes.
parameter, which can be extremely useful to, turn it on at the end, if you will, can be very, very effective in finding some local improvements to the best feasible you found at that point.
Yeah. For me, I would say, we often got a numerical trouble model. From customer. I would say, if it's continuous model LP, the chance is 60 or more than 60% are numerical troubling model. MIP less, but now what's my favorite is numeric forks. So just try it whether it addresses it. And then if not, then play with pre-solve aggregation, some other parameter.
Yeah, setting pre-solve equal to 2 can often be a helpful thing. And aggregation can often contribute to numerical instability. So if you're experiencing that, aggregation is a good thing to try, is to turn it off.
Okay, we'll move to the next question. What algorithms, techniques, and cuts are you thinking about, or do you find interesting at the moment?
Yeah, so non-convex MIQCP. That's a nice one because you can get so much nice performance improvements with so little work. So that is making my day quite often in the recent months, and I think for Ed it's the same.
Yeah. I think there was a stretch of like 3 days where I tried 3 things and they were all a win, which for MILP that never happens. It's like for MILP, it's maybe 1 out of 5 ideas where it's a win, if that.
More like 1 out of 10, but it's
Yeah.
I think that was the time I worked on MIP. That was easy also. I mean, that was like 2 or 3 years ago. Now I look like Ed, Toby, you are having fun with non-convex MIP. So now I try to see now LP, whether LP has something we can improve.
Okay, the next question.
Now we have to go back focusing on MIP. So I'm now back to MILP performance improvement, and I'm currently looking at conflict analysis and how to tweak the dual arrays to get things better. So that will be the next one that I try.
Okay, the next question changes subjects, may have been covered, but it might be worth asking again. So for solving NP-hard problems, are you planning to develop robust heuristics under Gurobi Optimizer? In particular for TSP, VRP, actually I don't understand that term, but in general, are we adding new heuristics for dealing with these particularly hard problems?
Yeah, so we touched on this a bit earlier. So I'd say in general, for the most part, we avoid diving too deep in any one particular pure type of problem. So, pure TSP, pure vehicle routing. And, the techniques you mentioned, taboo search, simulated annealing. So if you look inside the code, there are things that are maybe not exactly those, but are inspired by those. And so it's not that we don't have those, but if you're asking, are we taking all the techniques that have been proposed for solving specifically TSP? No, because as I mentioned earlier, it's rare for a problem to stay pure. It's our experience is it's quite typical in production applications for something to start out as something and then just morph, and all of a sudden it's a TSP plus something or a VRP plus something. And then the techniques, for the most part, the techniques that are specialized to the pure version, it's not clear how to extend them.
So for the Lin-Kernighan part for TSP, so we do have the general like 2-opt scheme for MIP, right? So that's so to say half of the Lin-Kernighan, I would say, right? But other than that, is there more? I don't think so.
The next question comes from Philip Taffet. He says, I've noticed that for many issues, the advice is to reformulate the MIP. Is there anything solvers can do or any feedback it can provide to help give guidance about how to reformulate a difficult MIP and to make it more tractable?
Oh, Bob, I guess that can you answer?
Ed, that sounds like it's good for you, frankly.
Yeah, I mean, that's the dream, right? So the dream is to be able to say, well, here's my problem. And for the solver to say, well, I see the problem you stated, but the problem you really wanted to state was this one instead. I mean, pre-solve does a little bit of that. When it comes to piecewise linear, that sort of thing, we sometimes will go say, well, yeah, you stated it this way, but it's better to state it that way. But in terms of sort of big, instead of this approach, to formulating this type of problem, you should use this approach instead. That's kind of that's a holy grail. So we're far from that.
And that can also like be bad if we do it in an extreme way. So let's take piecewise linear constraints as an example. So there are, I think, at least 4 or 5 different ways of modeling a piecewise linear constraint. So one involves a series of binary variables. Another one is using an SOS2 constraint, and so on. And it is actually possible, and we do that, to identify from the structure of a model that here someone is actually modeling a piecewise linear constraint on a set, or on say two variables. And then we could rip out the user model and replace it by what we think is the best way to model a piecewise linear constraint. But in reality, there is no single best way to model it. It really depends on the structure of the rest of the model, which one works best. And if we would do that, so like discarding the user approach and always use what we think is the best, then we would kind of remove the possibility of the user to pick the best formulation in his situation, in his or her situation. So that could be bad, even though it would potentially help overall on all of the model sets.
Okay.
Yeah, but overall, modeling is really an art, so that's really a tough question.
Is it fair to say, I mean, coming from the support side of the business, is it fair to say that we do that for numeric issues sometimes as well? And we are reformulating in a sense.
Yeah, in place of it's, you can consider it's not just the reduce the size, it's also reformulate. I mean, make big M smaller, and sometimes we'll translate SOS constraints into the regular MIP constraints by introducing binary variables, additional variables.
Yeah, sometimes pre-solve makes it worse, though.
Yeah. It's, I mean, it's hard to predict. We just
so it's I agree. It's about making it smaller and making it, and when possible, making it numerically better. But given a choice, we make it smaller.
Yeah, but somehow for me, making it smaller is not the thing that makes pre-solve the essential tool that it is these days. It's the fact that it tightens the formulation. Yeah. I mean, if you look at linear programming, for example, to a reasonable approximation, if you didn't do pre-solve, would it really change the set of solvable models? I think it wouldn't change it significantly. Speeds things up.
Just makes it slower, but
yeah. Right. But for MIP, it really, a lot of those logical reductions that get made in pre-solve, if you didn't do them, the solver wouldn't be able to solve the problem. Period.
True.
Yeah, true. I mean, it's even for LP, it's could be bigger. I mean, if you're talking about big supply chain problems, often, I mean, now it's maybe tens million variables or constraints, and pre-solve sometimes can make the problem 1,000 times smaller.
Absolutely.
Yeah.
Yeah, but it still is hopefully just a polynomial reduction in the solve time.
Yeah, theoretically, yeah.
Okay, that was a clever comment. Very good.
Yeah, but it is not only theoretical. I think I agree with Bob here that it's also from a practical point of view. It does make LP pre-solve does make the problem faster to solve, but it is not the point between solvable and unsolvable, not so much as it is in MIP. So in MIP it could be dramatic, the effect. But even more so, coming back to the original question, picking the right model formulation as a user, that is even more important than the internal pre-solving methods.
Okay, next question.
As long as we're talking about modeling, what's the advice on when to specify variables as integer valued and when not, when you can get away with it? Is there some general advice to be given there?
Yeah, I would say if integrality is crucial for your application, then you have to specify them as integers.
Oh, sure.
But if you're dealing like with millions of dollars in your variables, then it is not really important whether you measure this up to the cent in integral quantities. So that is more a continuous variable then.
Yeah, but I think to a first approximation, so I would say it's probably best to be conservative about labeling variables as integers, because so if they are integers, we will figure it. Well, in most cases, we'll figure it out. So if they're implied integers, we have a pass in the MIP solver that just goes and identifies those. And if you label some things as integers that are don't necessarily need to be integers, you may complicate the model quite a bit.
Yep, and just to go back to Toby's initial comment, it's the last thing in the world you want is a general integer variable with large bounds.
Yeah,
that's just a killer.
Bound bigger than the integer value.
Oh yeah,
yeah.
There's another question here. Can we expect any tools for column generation in the future?
Column generation, yes. Branch and price, no. So difference is, so column generation you can already do right now, which in my terminology means to solve the root LP using column generation. So you just use the Gurobi LP solver, add some more columns using the dual solution with your own pricing algorithm, and then repeat. And at some point you can no longer find additional improving columns, or you don't want to add more columns. And then you just stop, and then you introduce integrality, and then solve this as a black box MIP. So that's certainly already possible, and there are many applications that do this. Of course, that means that in the end, whatever solution you get, it's not necessarily a proven optimal solution, because it could be that at the local nodes of the search tree, you would have needed to add more columns to the problem, and that is not supported by Gurobi, and I don't think that we will ever support that, because this makes the whole code design so much different and so much more complicated. So that would be a very big development effort.
Okay. Next question. Callback functionalities are currently available in Gurobi. I'll skip a bit of that. Are there any plans to expand this set of functionalities, including adding branching callbacks?
So branching callback is relatively difficult. We could add, we have some ability for user to specify branching priority, and but the callback is tough with, we are doing some called dynamic search or restart the tree change, and also parallel and make sure it's deterministic is challenge. Could do, but based on our feedback after introducing the pseudo cost and using pseudo cost, usually it's really hard. Anything is hard to beat pseudo cost branching or later adding, reliability. It's also based on pseudo cost branching. It's hard to beat. So that's a question. So always struggle. We are struggling whether to add it, because it's a lot of effort. How many people really will find it useful? We are still not sure.
Okay. Next question. Has Gurobi been used to solve cliques? Believed NP hard, e.g. I'll let you read the question. It's in the Q&A session, but reading it verbatim, I think will be confusing. So
yeah,
it's about clique cuts.
It's just asking about the max clique problem. So I think it's more than believed NP hard. It is NP. Well, it's NP complete. And MIP, MIP is NP hard. So you can formulate lots of different NP hard, NP complete problems as MIP. And the formulation for max clique, you can just state it as a MIP. It's actually a pretty simple MIP to state. It's a hard MIP. among all the different MIPs that people solve, I actually don't have a sense of whether this is particularly hard. But yeah, I mean, I don't think there's anything so unusual about this problem. It's you formulate it, you pass to the MIP solver, and I guess we find a very high quality solution very quickly. I think it's really a question of how long it takes to find a proven optimal solution.
Yeah, and of course we separate clique cuts, which are of course the most important ones for those problem types. Other cuts developed for this, like odd wheels and odd holes and stuff, we don't separate, but some of them I think you can get through MIR.
Yeah, odd holes.
Odd
hole we've tried, and that's actually a loss. So that seems to be dominated by 0.5 probably.
Yeah.
Next question. While solving a problem, we found and developed, or I gather they specified a lot of bounds for integer variables, and this works for MIP, yet the linear relaxation was disastrous. How would you suggest would you suggest to add these as lazy constraints instead?
Boy, this sounds like an unusual situation.
Yeah.
So adding bounds on variables as lazy constraints, that seems to be unlikely to be a win. I'm guessing this is going to be what you're describing is particular to your model. In general, having good bounds on integer variables is valuable, and there's some cases where it can make the relaxation go slower. In general, I think it makes the relaxation go faster.
My guess, probably you add the bound, then the aggregation may be less powerful. Because aggregation, if you don't have bound, then could be more aggregation makes the place of smaller. That's my guess. Usually we never heard. This is rarely we heard such issue. Yeah. That's my guess.
Yeah, but if you want to send us the model, we'd be happy to take a look and see what's going on. Yeah. That does sound strange, unusual.
Yeah. All right. Before we're coming near to the end of our time, so we do have a number of questions we won't be able to answer. Do any of the panelists have questions they'd like to pick from the remaining? You can have a look at that, and I can proceed with another question we have here for now.
Well, I know there's one question on here about the biggest MIP we've ever solved and the smallest one we can't solve. So seeing that, I did a little bit of checking. And the smallest one I found that this is actually a model that we had from a customer at CPLEX. And as of 2008, when we left CPLEX, it was unsolved. We don't have access to it now, so I can't say with absolute certainty it's still unsolved, but I bet it is. This is a problem with 44 constraints and 51 variables. And the problem with that model was that all 51 variables are general integer variables with no bounds. They're all free variables. If you take and put any sort of reasonable bounds on the variables, it solves quickly. But if you don't, it's still unsolved as far as I know.
Yeah, I think you could also, Bob, I think you could also have a single constraint, equality constraint, so like a subset sum problem with, I don't know, 60, 70 variables or something like that. That is probably also very hard.
Yeah, could very well be.
Like a Markov model.
Yeah, but Markov with binaries, right, yeah.
Okay, yeah. Well, I wanted to take a customer model.
Yes,
Wanted to take customer models, and that was a customer model. It was from a bank, a French bank. So you can take that for what it's worth. When you ask the question, what's the biggest model? There's a question of how you measure what's the biggest model, right? Number of constraints, number of variables, number of non-zeros are three measures that come to mind. So I checked, and in terms of the number of variables, the biggest model we've ever solved had about 1.3 million constraints and about 115 million variables. It's a dating application.
That was an LP or a MIP?
It's a MIP. These are all MIPs.
Oh.
This was a MIP, and we solve it essentially with defaults in about 13,000 seconds. The problem with the most constraints, based on my testing that we've solved, and I have no idea where this application comes from, but it is from a customer, had 57 million constraints and 41 million variables. And it actually solves to optimality in 331 seconds.
And that is on your new fancy L cluster machines, or where did you solve that? Or
I had to solve it on the K cluster.
The memories, yeah. Okay.
Just because of memory. But in this particular case, it's pre-solve just totally annihilates the problem.
Yeah.
That's why we can solve it so fast. That's not why we can solve that dating one so fast. Pre-solve doesn't reduce it to something trivial. And in terms of non-zeros, the biggest one I could find had roughly 400 million non-zeros. It's a private aviation application. Solves in about 8,000 seconds. So we actually in our model set, we have 700 and last time I checked, 797 models from customers with at least either 1 million constraints or 1 million variables, or both. And from those, I actually ran some tests using defaults and a 30,000 second time limit, and roughly 500 of those 797 models, so million-sized models, if you will, solved optimality with defaults in 30,000 seconds. That's pretty impressive. We get a lot of big models these days.
Yeah, and then we have, of course, we've got for testing, we've got some synthetic model generators where we generate models with, I think, 250 million variables and a few hundred million constraints just to make sure nothing breaks.
Yeah.
But
2 billion non-zeros more.
yeah.
These are all,
generally.
the ones I was using are all customer models, quote unquote.
Right.
What's the record? Any smallest model we cannot solve? Not from.
You mean
three variable models? I still wondering.
Probably three general integer variables. So it needs to be general integer then.
Yeah.
It's a challenge for the audience. Come up with the smallest model that can't solve.
Yes. Please send.
Well, the smallest model that I've found that we can't solve if you turn off pre-solve is got like 2 constraints and 3 variables.
Yeah. My conjecture is 3 variables.
Yeah, without pre-solve where you have this.
Without.
Death, right?
Do I hear 2? 3 variables going once, going twice?
So Blair, do you want to wrap up?
So great job, everybody. This was definitely an interesting discussion with lots of great questions. And thank you to Ed, Gu, Bob, Toby, and Dan. And thank you to everyone for joining.
Goodbye.
Bye.
Goodbye.
Bye. Bye.